This lecture video, what I want to do, you can see the title in the upper left-hand corner, is explore the field of a solenoid to just get a feel for, the field. How does it build up? So here's how I'm going to approach this exploration. Over here in black, you can kind of see that I've sketched out a coil, or a solenoid. And if you count the number of circular turns, I don't know how many there are, maybe there's like 20 or something like that. But what I've done is I've outlined in red 3 separate coils. And each of these coils for this ideal solenoid is a circle, right? It's a single circle carrying a current. We could say the current is I. So here comes a current, and it runs along the coil and also out to the other end of the wire that makes the coil, right? But here are 3 different coils that are highlighted. Each coil is a circle. So here is a coil. And each coil has the current run on the coil in the same direction. And it looks kind of like the way the coils are organized in this drawing. Kind of wish that I didn't. Did I draw it that way? Anyways, in the drawing that I'm showing you, it looks like the coil current is, coming in the back of the solenoid, wrapping around the top, and coming around the front of the solenoid and going under the solenoid to the back again. So, it appears to be flowing in this direction. So it's coming around the back of the solenoid and now going up and around the solenoid in that direction. I hope you can see these little 3D arrowheads telling you the cycling sense of the current. Yeah, and so by the right-hand rule, the magnetic field is going to cross on the inside of the coil this way. That's what the right-hand rule is going to say. So the field lines are going to look like this as they come through the coil. But if you check at places outside the coil, say above the coil, those field lines actually run in the opposite direction. But they have to be complete cycles, right? Each of these field lines is actually a cycle with no end. That's an important detail about magnetic field lines, is they never end. They don't start anywhere and end anywhere. They are always full cycles. And so if you follow the magnetic field lines through, it's the same on the other side, right? An important detail is the field is strong if you get real close to the wire, right? So the field is real strong close to here, but as you go out, as you go further and further out, it's weaker elsewhere. So I'll say it's weaker out here, but it's also weaker out here. And if the further and further away you get, the magnetic field at infinitely far from the center of this coil, the magnetic field is going to be 0, very, very far away. Because very, very far away, it's hard to physically see that there is a current that's cycling at all. So it doesn't even look like there's a current. So there won't be a magnetic field way out there. But it is very strong in here. And it's important to notice that when you're really close to the wire, if you're on the outside of the circle, the field runs one way. And if you're on the inside of the circle, the field runs in the opposite direction. And likewise, on the left and the right-hand side, if you look at a place like here, the field goes down to the left. And if you look at its sort of mirror image over here, the field goes up and also to the left, right? So the field has a very interesting set of directions just for a single circular coil. So the point is, if I want to understand the magnetic field of the entire solenoid, then what I need to do is try to understand how the magnetic field is going to superpose for every single coil. And the coils are at different locations, right? Here's a middle coil, here's a coil on the right side, some distance away, a coil on the left side, some distance away. And what I'm going to do is I'm going to exploit patterns, like I'm going to use some symmetry arguments to look for cancellations of field, right, where the arrows seem to point in opposite directions, and look for reinforcements of the field, right, where the arrows seem to point in the same direction instead. When they point in the same direction, they add in a constructive sense. And when the arrows point in the opposite direction, the way they add is a destructive sense. Okay, so I actually drew some of these images that I'm alluding to up above, so forgive me for doing this. But I've drawn the magnetic field of a single coil. So the single coil is in black, and the current actually is running in the same sense. Can you see that at the bottom of the coil, it's sort of headed out of the screen? At the bottom of the coil, see the current is coming around the bottom, coming out of the screen. So it's the same sense of current flow. Okay, so here is this current carrying coil, and it's a single coil, right? And what I've done is I've drawn the magnetic field, but only the magnetic field in the upper half of the coil. Not due to the upper half, it's actually the field due to the whole coil, but I've only drawn the magnetic field lines in the upper half. Here are the magnetic fields in the upper half and the lower half together. But I'm only going to worry about the upper half because the lower half field is going to combine in the same way, because the lower half field looks like the upper half field. So these blue wide lines are the field lines. And I've put little direction indicators, right? Through the middle of the coil, they head left. Up above the coil, they actually head towards the right, right? And there's lots of directions in between. I also, in red, right, this line right here, you can see is a line that's kind of interesting, and I pointed out some locations. Here's a location, another location, another location, another location, another location. And what I've done below is I've redrawn the red line, but I've indicated the magnetic field vector. These are the field vectors outside the coil, right? These are the field lines up here. These long blue lines are field lines. Those aren't field vectors. But the field lines, there's a way to read them, right? Where the density speaks to the strength and the direction speaks to the direction of the vector arrows. And you can see that what I've drawn is the vector arrows. The strongest magnetic field vector is going to be right here. Can you see where I'm drawing? And that's because this is the place along the red line with the highest density of field lines. You see all the field lines local to here? But at the field arrow, can you see that it points towards the right? Because the field line is passing through that location towards the right. So I've drawn the longest arrow towards the right. And if I go look at this position right here instead, right? This position, if you look at the arrow, right, the field line is crossing downwards through the red line, that location. So I just drew a smaller downwards arrow. That's the magnetic field vector there. And if I go look at this position instead, can you see that the field line is heading down to the left? But it's a place of very low density of field lines. So this is the weakest or the smallest vector, magnetic field vector I'm going to draw. And likewise, this one here gets drawn here, right? And this one here gets drawn here. And you can see how the arrows go, right? Okay, notice that this line is above the coil, right? This is above the coil. I could also draw a red line inside the coil. But what's going to be interesting about the red line inside the coil is everywhere I ask what is the direction of the magnetic field, it's going to mostly be leftward. It's going to be towards the left, right? That is, every arrow, every vector I draw for a red line that goes through the middle of the coil, the vector arrows only point left. But if you go above the coil, the arrows can actually point up or down, right or left, right? That's pretty interesting. Okay, and that speaks to how the magnetic field can add up to 0 outside the coil and not add to 0 inside the coil. So this red line represents being outside the coil, and this central line is inside the coil, right? Okay, so what I've done is I've taken this, this drawing up here, and I copied and pasted it overlapping. And the reason I do that is I'm trying to understand how the superposition is going to happen, right? How is the superposition going to happen? So it's sort of tough to read it, but can you see that everywhere inside the coil, right? So this is just in the sense that I have 3 cycles represented. I just drew those 3 cycles up here. And you can see that down inside of the coil, can you see that everything seems to be flowing towards the left? All of the magnetism seems to be leftward. But on the outside of the coil, it's a little different. But I'd like you to see something that's pretty interesting. I'd like you to notice that where this coil goes up, this coil is coming down with the same strength. So these are cancellations of up-down. And these cancellations, you can imagine, happen between every pair of circles, right? Every pair of black circles away from that position. So you just go outward from that position and you will always get that cancellation. So there is no up-downness to the magnetic field outside. So the magnetic field that you might suspect points either away from the solenoid or towards the solenoid, those arrows always cancel. Also, you can see that there are places where the field is going to be added towards the right. These places here, right? But the interesting thing is look at how much other field there is that points towards the left. Do you see all that leftward field? So all the leftward field and all the rightward field are going to sort of destructively superpose. And it's interesting, but it works out exactly that the magnetic field on the outside is just going to add to 0 everywhere, including this position, this position, this position, this position, no matter where you go out in space, over here, over there. If you take into account all infinite number of these circular current carrying loops, if those current carrying loops are uniformly distributed, so that is a uniform density along the solenoid, then everywhere you check that's outside the solenoid is going to have full cancellation. If there is a magnetic field vector in that direction of that strength, there's at least 1, maybe more, that add in the other direction, and they cancel. And this direction cancels with magnetic field contributions from the other direction. So the magnetic field is simply just going to cancel everywhere outside the solenoid. Yeah, so this video is by no means a mathematical proof. So nothing I've shown you is a proof. I am only trying to motivate how to superpose magnetic field lines or fields from different coils. And there are cancellations outside the solenoid and only reinforcements inside the solenoid. So inside the solenoid, the magnetic field cannot be zero. And outside the solenoid, the truth is I can't say that it is zero, but I can say that there are lots of cancellations. And so thinking that the magnetic field could be zero is plausible for the outside. Okay, thanks. So in a following video, I'm going to use Ampere's law to prove these assertions about the magnetic field of a solenoid. Or at least in the sense that a physicist proves anything with math, right? A mathematician would watch this happen and maybe throw up in their mouth or something, but yeah.